Let's do a few examples of Lewis structures, and let's start with something pretty basic. First of all, let's just try something simple to get started, like water. And the first thing that we need to do is to add up all of the valence electrons. That's what we do. We sum all of those up. And if you look at the periodic table, we're looking for hydrogen and oxygen. So yeah, you can see that. Oxygen is over here, and oxygen is an S2P4, which means that it has 6 valence electrons. So you want to use your periodic table when you're counting valence. And we see that the noble gas before oxygen is helium. And then we see that oxygen is in the second row, where we have, it fills the 2s1, 2s2, and comes over. And we have 2p1, 2, 3, 4. So we have 2 s electrons, 4 p's, and that's a total of 6. Hydrogen, of course, is just a 1s1, and so it's only bringing 1 valence electron. So I have 2 valence electrons from the hydrogen total and 6 electrons from oxygen. And so I don't need to remember where they came from. They're all thrown into the pot. First thing I do then is arrange the atoms in the way that I'm pretty sure that they're bonded, and of course for water we know that. And I'm not implying here that the molecule is linear. Lewis structure tells us nothing about bond angles or geometries, just about bonding pairs and lone pairs and where they are. So after that, I want to make single bonds between the atoms that are bonded together, and I'll draw a shared pair of electrons instead of a pair of dots. I draw it as a single bond, so that counts for 2 electrons, and so does this. So when I draw it, you'll hear me saying 2, 4. I've got 4 electrons left over. I want an octet around each of these atoms. However, I know that hydrogen is an exception to that rule and only wants 2. It can only handle 2, so that one is actually complete. So I want 8 electrons around the oxygen, therefore. So I have 2, 4, 6, 8. Some students will choose to draw a pair of electrons as a line here as well, whether it's bonding or non-bonding. You can do that. I just like to differentiate between bonding and non-bonding by writing a shared pair as a line, a bond stick, a single bond stick, and writing a pair of dots as a lone pair. So there's someone at my door, and they've gone. Okay. So this is my best Lewis structure. I have 2, 4, 6, 8 electrons, and I can't do anything more with this. I have 2, 4, 6, 8 electrons around the oxygen. I have 2 around hydrogen, 2 around hydrogen. So when I'm counting this pair, I count it for hydrogen. When I count here, I count this pair as belonging to oxygen. When I count here, 1, 2, 3, 4, 5, 6, 7, 8. So I do have the octet satisfied for oxygen. One thing we need to be able to do as well is formal charge. And so let's just do it here for practice. The formal charge is equal to the number of valence electrons. So for hydrogen, it's 1, minus half of the bonding, and that's 1, plus all of the lone electrons, non-bonding electrons, and there are 0. So 1 minus 1 minus 0 is equal to 0. So for each formal charges, here we go, hydrogen equals. So for the hydrogen, I have 1 minus 1 minus 0 equals 0. And for the oxygen, I have number of valence is 6 minus half of the bonding electrons, or if you like, the number of single bonds. Half of the bonding is 2. And I also want to subtract all of the non-bonding electrons, 1, 2, 3, 4. 6 minus 6, 0. The sum of the formal charges, so 2 zeros for the hydrogen, a 0 for the oxygen, is equal to 0, which is the charge on the molecule. Of course, it's neutral, and so that all adds up as well. Okay, so that's our first straightforward example on H2O. Excuse me. Let's try ammonia Nh3. Ammonia has nitrogen and hydrogen, so just looking for hydrogen here. Any element in this group is going to have 5 valence because it's an S2P3 configuration, and of course the hydrogen has 1. So I have 3 valence electrons total from hydrogen, 5 from the nitrogen, and so again I've got 8 electrons to arrange around these atoms in this molecule. So I have nitrogen, H, H, H. And just arrange your hydrogens around your nitrogen. Make single bonds, 2, 4, 6, and then I want to continue. I have 2 more electrons, or 1 pair if you like, and I want to satisfy the octet around all of the atoms, but I don't around hydrogen because it only wants 2. So in fact I'm going to put that pair here. And once again, this is my Lewis, my best and my only Lewis structure. 2, 4, 6, 8 electrons around nitrogen, the octet is satisfied, 2 around each of the hydrogens, and that's great. And if I want to look at formal charges again, I would say that for each hydrogen, because it's equivalent, I have 1 valence minus half of the bonding, 1 electron, minus 0 for the number of non-bonding electrons, and that is equal to 0. So the formal charge on each hydrogen is 0. I'm expecting that the formal charge on nitrogen is also 0, because the molecule doesn't have a charge, and they're supposed to add up. So I have 5 valence minus half of the bonding, which is 3, minus all of the non-bonding, which is 2. So I end up with 5 minus 5, and that is 0. So all of that is looking good. What do I do when I have an ion? Let's look at NH4+. So now I have 5 from nitrogen, 4 total from hydrogen, 5 and 4 is 9, and then adjust for the charge. So it's 9 minus 1. I've got 8 electrons again. N, H, 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 2, 4, 6, 8. And because this is an ion, I put it in square brackets with a plus outside. So I know that this is a charged species. This is one of our polyatomic ions, the ammonium ion. The formal charges now should add up to a +1. So the formal charge, what are they? For each hydrogen, because they are equivalent, I've got 1 minus 1 minus 0 is 0. And for nitrogen, I have 5 valence electrons minus half of the bonding electrons, 4, minus all of the non-bonding electrons. I don't have any on nitrogen, so that's 0. 5 minus 4 minus 0 is +1. And so I'm actually adding up to the charge on the molecule. So that's my Lewis structure for the ammonium ion. Let's look at carbon monoxide. Carbon monoxide has a total number of valence electrons equal to 10. 4 from carbon, 6 from oxygen. Look at your periodic table. Oxygen is an S2P4, so it has 6 valence electrons. Carbon has 4, so for a total of 10. Carbon and oxygen are bonded together, 2, and then 4, 6, 8, 10. What do I do with this? Well, on our instructions for drawing Lewis structures, it says use multiple bonds if necessary. So if I take this pair and put it here, that allows me to count it when I'm counting for oxygen, and it also reserves the counting of it when I count for carbon. So where I already have 2, 4, 6, 8 electrons around carbon, which is happy, I only have at present 2, 4 around oxygen. So if I share this one, that'll bring that to 6, and if I share this one as well, that will bring this to 8. And I've reached my maximum in multiplicity of a bond, because I can only have a maximum of a triple bond. So my Lewis structure is going to be, it's kind of in progress here. I have a triple bond, and I'm left with a lone pair on each one. You see what I've done? I still have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. Great. But I have 2, 4, 6, 8 around carbon and 2, 4, 6, 8 around oxygen. And I really don't have a choice in the structure. This is my Lewis structure. To do the formal charges, let's look at carbon. Carbon has 4 valence minus half of the bonding, and I have 6 bonding electrons, or if you like, 3 bond pairs. So half of those bonding electrons is 3, minus all of the non-bonding electrons. So 4 minus 5, that's a minus 1. And the formal charge on oxygen is 6 valence minus half of the bonding minus the number of non-bonding, and I have 6 minus 3 minus 2, which is a plus 1. It adds up to 0, which is the charge on the molecule, so everything is a-okay. All right, let's try one more, and then we'll maybe make a new video so none of them are too long each. Let's move this paper up. All right, let's try, what do I want to do next? Let's do, let's do another ion, polyatomic ion. We've got ClO minus. A halogen. A halogen is one short of the noble gas, which has 8 electrons, right? As a group, the halogens are right beside noble gases, and they have configurations, valence configurations of S2P5, which is 7. So I have 7 from chlorine, I have 6 from the oxygen. 7 and 6 is 13, and you might be wondering, that's an odd number, but I also need to add one more because it's a negatively charged ion. So I have 7 plus 6 plus 1, which is 14 electrons. Chlorine is clearly bonded to the oxygen. I only have 2 atoms in this species. And I'll make a single bond, 2, and then I want to use up my 14 electrons. So I have 2, 4, 6, 8, 10, 12, 14. That looks great. I've got 2, 4, 6, 8 and 2, 4, 6, 8. It's an ion, so remember to draw the square brackets and to put the charge outside. And let's just see if that's the formal charge is as close to 0 as I can make it. The formal charge on chlorine is 7 valence minus half of the bonding, which is 1, minus all of the non-bonding, which is 6, and that equals 0. So I'm anticipating that my single bonded oxygen is going to have a formal charge of -1 because the sum has to add to the real charge on the species. Oxygen is 6 valence minus half of the bonding, which is 1 electron, minus all of the non-bonding electrons, 2, 4, 6. And of course that equals -1. So 1 chlorine and 1 oxygen total to a -1, which is the charge on my polyatomic ion. So that's great. I think we have room for one more. Let's just do one more. One more simple one, and then we'll get into the exceptions. Let's do C, double bond O, H, H. It's a funny one from the book because it kind of looks like it's already done. So it wants us to make the formal, or sorry, the Lewis structure. Well, this would be written as CH2O. And they've already drawn it for us. I probably would not have drawn it for you in a question. I would just give CH2O. So let's work with that. CH2O, I've got 4 electrons, plus 2 is 6, plus 6 more is 12. And I know that I have the atoms arranged this way. Single bonds, 2, 4, 6. Hydrogens are done, 2, 4, 6. I want to put this as 8, but I never do my central atom first. I always do the outside one. I'm not doing these outside ones because they're hydrogen and they've already maxed out. 2, 4, 6, 8, 10, 12. So I'm deficient here on the carbon. So what I do is I take one of these and share it so that I have a double bond. And that becomes a double bond to the oxygen, and I still have 2 lone pairs left over. So when we become very familiar with doing these, we would have looked at the first structure in the first place and said, oh, hydrogen has 2, that has 2, carbon has 2, 4, 6, 8, good, oxygen has 2, 4, oh, I'm missing 2 lone pairs. So whenever we have oxygen, and you'll see whenever we have nitrogen, they always have an octet of electrons. So when they're deficient in bonds, like carbon has 4 bonds, 1, 2, 3, 4, I always check that carbon has 4 bonds, that hydrogen has 1, and now I'll be checking that oxygen and nitrogen each have 8 electrons around it, but that'll be from a combination of bonds and non-bonding electrons. Yeah. So here it is from scratch, but I think soon we'll be in a position to just look at this and go, oh, I need 2 pairs of electrons, one here, one here. Anyway, that's good, and for the sake of completion, we'll do the formal charges for each of the hydrogens because they're identical. I have 1 minus 1 minus 0. For the carbon, I have 4 minus, half of the bonding here is 1, 2, 3, 4, minus 0, non-bonding. And the oxygen, 6 valence minus half of the bonding minus all of the non-bonding, 0. The sum of the formal charges is the charge on the molecule, which is nothing. And that's the beginning of our practice of structures.